Welcome back, and this is part C of concept video for section 10.2, which is calculus with parametric curves. Let's see one more example for finding the length of or arc length of a curve in parametric form. So we will choose again the length of one arch of the cycloid whose equation in parametric form is given by x equal to r times theta minus sine theta, y equal to r times 1 minus cosine theta. So we will start with our formula for length of the curve, which is integral alpha to beta, which is the initial and final value of the parameter, then dx by square root of dx by dt the whole square plus dy by dt the whole square dt. In our problem, in this particular problem, the parameter is theta, so we would use the parameter theta. Now, x is given to be r times theta minus sine theta. So we will find out dx by d theta, which is r times 1 minus cosine of theta. And y is given to be r times 1 minus cosine of theta. And when you do dy by d theta, it is r times 0, then minus of minus sine theta. So it is positive sine theta. And theta, because it's one arch, because it says it's one arch. Earlier when we graphed the cycloid and we said that the arch of the cycloid, when you take one arch, theta is from 0 to 2 pi. So we have seen that in one of the examples before. So here it is, in x it is 0 to 2 pi r. In terms of theta, it is going to be from 0 to 2 pi. We have used this idea in even in this problem. So we change this to 0 to 2 pi. So for one arch of the cycloid, theta runs from 0 through 2 pi. It makes one complete rotation of the coin. So that will be 0 through 2 pi. So let's plug in these values into our formula L, which is integral 0 through 2 pi, and a square root of dx by d theta the whole square, which is this one, then dy by d theta the whole square. So we have to square that one. So it's going to be r square 1 minus cosine theta the whole square plus r square sine square theta d theta. So we can take r square out. You can take r square out but it is within the radical. So when you pull it out of the radical, it becomes just r integral 0 to 2 pi square root of 1 minus cosine theta the whole square plus sine square theta. So we have to reduce that. It's r outside, integral 0 to 2 pi. Then expand this 1 minus cosine theta the whole square. This is 1 minus 2 cosine theta plus cosine square theta. Then outside you have sine square theta. Um, everything within the radical d theta. This integral 0 to 2 pi with r outside. Then you can use Pythagorean identities. You say that this part is equal to 1. This part is equal to 1. So you have 1 plus 1 added. So that will become 2. 2 minus 2 cosine theta. Square root of that d theta. So in this, you can write 2 times 1 minus cosine theta. But 2 is within the radical. So you can pull that 2 outside, root of 2 outside. So you'll have r times square root of 2, then integral 0 to 2 pi, square root of 1 minus cosine theta, theta. Now, if you keep the integral as is, it's hard to integrate. So we have to again use some trig identity which helps us to write the way we want to write. So we know that there are two formulas we often use. One is sine squared theta. We write that as 1 minus cosine 2 theta over 2 often. Whenever you want to integrate, even exponent of a sine or cosine. So in this one, if you have theta here, then it is double here, right? So it is double. Then if I write half of this, then I have to double 2 times half of whatever I write here. So if you have theta, becomes double, right? In this case. Whereas theta by 2, it becomes double theta by 2, of course divided by 2 is missing, it has to be written there. So what is sine squared theta by 2? It is equal to 1 minus cosine of 2 times theta by 2, that is just theta, divided by 2. So if you notice here, what I have in this part is 1 minus cosine theta, which is 1 minus cosine theta over here, so which is 2 times sine squared theta by 2, that is 1 minus cosine theta, if I move this 2 to the left-hand side. So that is one way of writing the expression inside the radical, that is r square root of 2 already there. Then it is integral 0 through 2 pi, then square root of 1 minus cosine theta becomes 2 sine square theta by 2 d theta. So there is one more radical 2 coming out. So it is r radical 2 times radical 2. Then you have integral 0 through 2 pi. Square root of sine square, that will be absolute sine theta by 2 d theta. But when theta lies between 0 and 2 pi, so you notice here theta lies between 0 and 2 pi. So if I divide everything by 2, I will get theta lying between 0 and pi. Theta by 2 lies between 0 and pi. So that means theta by 2 is an angle in the first quadrant or second quadrant. So in either case, sine is positive. So in both quadrants, sine is positive. So I can take, instead of writing absolute sine theta by 2, I can simply write sine theta by 2. I can take off the absolute sign because it's positive. So now the problem becomes very simple. Sine theta by 2, integral of sine theta by 2 is negative cosine theta by 2 divided by 1 half between 0 and 2 pi. So it is equal to negative 4r. If I flip and multiply, then it is cosine of 2 pi over 2, that will be pi, and then minus cosine of 0. So it is negative 4r, cosine pi is negative 1, cosine 0 is 1. So it is negative 4r times negative 2, that is equal to 8r. So in the picture shows here, when the coin rolls along the horizontal line through one complete rotation from 0 to 2 pi, the length it traverses, which is this part, is actually the length of the curve, which is 8r. The last part of the section is about surface area. So you notice that in this section, you're learning a lot of information. Um, the horizontal tangent, vertical tangent, writing the equation of a tangent line, and then you saw area of a parametric curve, and then you saw length of a parametric curve, and then the next part is going to be surface area of the parametric curve. So it is kind of similar to the idea that you did in chapter 8 for Cartesian equations. When an arc is rotated about the x-axis and you find the surface area. When the arc is rotated about the y-axis, how you find the surface area and so on. In the same way as for arc length, we can adapt formula 825 to obtain a formula for surface area. Formula from chapter 8, section 2. If the curve is given by the parametric equations x equal to f of t, y equal to g of t, where t lies between alpha and beta, is rotated about the x-axis, where f prime, g prime are continuous and g of t is positive, then the area of the resulting surface is given by, which is rotated about the x-axis, is given by integral alpha to beta 2 pi y ds. ds is the arc length. There we had two options. Here we have only one formula for the arc length. It's kind of much simpler to do. So it is dx by dt the whole square plus dy by dt the whole square dt. If it is rotated about the y-axis, that is alpha to beta, so rotated about the x-axis previously, notice here it is y. It is rotated about the y-axis, then in the formula what do you expect? That's 2 pi x square root of dx by dt the whole square plus dy by dt the whole square dt. So when it is rotated about the y, you write x here. And then what is ds? The general symbolic formula s equal to 2 pi y ds rotated about the x-axis and s equal to 2 pi x dx, which is rotated about the y-axis. So notice here if it is x, it's equal to y here. This rotated about the y, it will be x. Are still valid, but for parametric curves, we use ds, which is the notation for the arc length, which is simpler than there. We had two options. We have to carefully choose the right one, but here there is only one. So ds, the arc length is dx by dt the whole square root of dx by dt the whole square plus dy by dt the whole square dt. Show that the surface area of the sphere of radius r is 4r square. So the idea is to parameterize a sphere. We have to write down an arc. We want to find out an equation of an arc in parametric form. When it is rotated about the x-axis or y-axis, you get a sphere. So that is to visualize the problem like that. So step one is to find a parametric an equation of a parametric curve when rotated about the x-axis or the y-axis, we get a sphere. Okay, so we will parameterize. We will find out. So if you think of a half circle or semicircle, and when you rotate, if you consider a semicircle, when you rotate this about the x-axis or the y-axis, you're going to get, if you rotate it about the x-axis, you're going to get a sphere. Or if you consider a semicircle like this, and if you rotate it about the y-axis, rotate about the y-axis, you're going to get a sphere. So when you rotate an upper semicircle about the x-axis, or right half of the semicircle about the y-axis, in either way, when you rotate, you're going to get the shape of a sphere. So we'll assume that these circles, semicircles, have radius r. So we will consider one of them. We will take this one for our example. So upper semicircle. So equation of a semicircle in parametric form. Equation of a semicircle of radius r in parametric form. Parametric form. So which is x equal to r cosine t, y equal to r sine t. If it was full circle, then a t would run from 0 to 2 pi. Because it is half circle, it runs from 0 to pi. Now let's find out, we'll apply the formula for surface area. Surface area SA is, we are going to rotate this about the x-axis and rotate about the x-axis. So surface area will be equal to integral 0 to pi, then 2 pi y ds converted to parametric form is what you have to use because it is rotated about the x-axis, so you have to use y. This ds here stands for the arc length in parametric form. So it is integral, surface area is integral 0 through pi, 2 pi y equal to r sine t, then ds is square root of dx by dt the whole square plus dy by dt the whole square dt. So we know that x equal to r cosine of t. So dx by dt equal to negative r sine of t. Y equal to r sine t. So dy by dt equal to r cosine of t. If we substitute them here, it is 2 pi r sine of t times square root of dx by dt, which is negative r sine t the whole square, plus dy by dt r cosine of t the whole square dt. So it is 2 pi r. Then you are getting here r square sine square t plus r square cosine square t. So r square can be common factored out, but it is within the radical. So square root of r square will be r. That also comes outside of the integral. Integral 0 to pi sine of t, then sine square t plus cosine square t will stay inside the radical, which will be equal to 1 by Pythagorean identity. So it is just integral sine t dt. So it is going to be 2 pi r square integral of sine t, which will be negative cosine of t between the limit 0 and pi. So it is negative 2 pi r square cosine pi minus cosine 0. So it is negative 2 pi r square. Cosine pi is negative 1. Cosine 0 is 1. So it is negative 2 times negative 2. So it will become 4 pi r square. In fact, we know that surface area of a sphere of radius r is 4 pi r square. We are proving this by calculus techniques and using parametric representation of a semicircle. Then in this section, suggested problems, I have shown problem number 7, 13, 29, 31, and 41 in the section video. Please refer to those. For section 10.2. In this section, you have learned a lot of information about calculus aspect of parametric curves, like finding the tangent, finding the slope of the tangent line, finding the equation of the tangent line. Now, what do you mean by what, under what condition one condition you say there is a horizontal tangent, under what condition will there be a vertical tangent, how to get the second derivative. Second derivatives normally help you get the condition for concave up or concave down. You will see some problems in the homework exercise and my section videos as well. And then how to find out the length of an arc, tangent line of the cycloid or any parametric curve, areas of the parametric curve, and then we saw arc length of the parametric curve, and also we saw surface area for the parametric curves. So we have seen lots of information about parametric curves in this section. And take a look at the additional problems in the section videos from the suggested problems. Hope these videos help.